Thank you. Thank you very much for the introduction. Thank you. I'm happy to be here. Great conference, lots of friends. Very pleasant experience. So my talk is about diamond models. I don't have a usual pointer, so I'll use my hands on the screen. I think the audience is not too big so that you should be able to see. So I'll start with the discussion of what diamond models are. So for a diamond model, one starts with a graph. And a diamond covering of a graph is a choice of a subset of edges so that they cover every vertex exactly once. And here are examples. And a diamond model is some way of assigning a probability measure to the set of all possible diamond covers. So diamond models are pretty old. They were introduced in 1930s in the chemistry literature. You can see the title of the paper was Statistical Theory of Perfect Solutions. They were not actively studied until 1960s, where they came into prominence because of their connection to the two-dimensional Ising model and its solvability. And in particular, for planar graphs, diamond models can be solved in some sense, namely that their partition functions can be computed in terms of Pfaffians and determinants. And there was a, sorry? I don't want to change it to full screen because I'll switch windows a little later on. So I'll do that when I can. Okay, thank you. Right, so I was saying that in 1960, statistical physicists actively studied diamond models, and they made very important contributions. In the 1980s, there was a standout paper by Nienhaus, Hilhurst, and Blotte, who suggested that diamond models have something to do with the physical phenomenon that's pictured on the image on the right. That's an actual photograph. That's not a cartoon. So these are helium crystals at low temperatures. The bottommost one is close to absolute zero. And you can see that the crystal has only flat faces. Now, when the temperature rises, well, a little bit, by a degree or two, what happens is that some of the flat faces start to curve. And moreover, that curved part fluctuates much more than the flat one. And that's not visible in the static picture, but that's what they observed. So this is actually the crystal lives in the superfluid helium, and they were able to take pictures. So this phenomenon of going from flat, rigid faces to curved and fluctuating ones is known as roughening phenomenon in equilibrium crystal physics. And diamond models were suggested as a mathematical toy model, essentially, for this kind of physical phenomenon. And I'm spending time on this because this will become relevant a little later. And so, as usual, mathematicians were late to the party. So since the late 1990s, mathematicians started to study diamond models from slightly different perspective than physicists did. Yeah. Okay, so that's the first line on the next. Which planar? So you can define diamond configurations on any graph, but determinantal of Pfaffian structures will only work, will work on planar graphs and on very few other examples. So planar guarantees the determinantal structure that's underlying. Right? Okay, so I will actually restrict myself to subsets of the square lattice. So that's one restriction. And then the second restriction is that I will only restrict myself to two types of the domains. Both are squares in the square lattice, one with the sides parallel to the coordinate axis and the other one with the sides at 45 degrees angle. Okay, so this is just a square, and domains of this shape are known as the Aztec diamonds. The term was coined by Jim Propp, and it's very nice, and it's stuck. Now, so these are examples of these domains of size 4 and 3 in this case, and examples of their dimer coverings, and they're not very nice to look at. If you look with the naked eye at a picture like that, you don't see much. So people invented tools to look at them in a more convenient fashion. So let me tell you what these tools are. So first, these graphs are bipartite. Well, the square lattice is bipartite, which means that you can split the vertices into black and white, and the edges always go between black and white. And that's nice. That's an additional structure that actually simplifies a number of things. In particular, once we do that on the square lattice, the horizontal edges will come in two types, those that have black on the left and those that have black on the right. And the vertical edges will come in two types, same thing, black on the bottom and black on the top. So we have 4 types of edges. That's the first observation. The second visual tool is that instead of looking at the edges, we will look at the domino tiles that cover these edges. So here on the right picture in the second row, there is there is a chosen domino cover, and then there are domino tiles drawn on top of the dominoes. And so instead of looking at the edges, we'll look at these domino tiles. And since we have 4 types of edges, we can take the corresponding 4 types of dominoes and color them in 4 different colors. And so this way we get a colored domino covering of a certain domain. Okay? So these are better to look at, more pleasant. And so the bottom row here is a random sample of the uniform measure on all possible domino covers or dimer covers of the square with the axis parallel to the axis and the 45-degree angles. Okay? So this is, these are actual perfect samples. One can find an algorithm to do a perfect sampling. And so the pictures are drastically different. You see that in the square on the left, there is chaos everywhere. There's not much to see, it seems. And in the picture on the right, there are these frozen pure colors in the corners. And then there is a curve, suspiciously looking like a circle, that separates the pure colors from the mixed colors. And then there is some change of average color in the middle as well. Right? So I will mostly be concerned actually with this picture on the right, the more interesting one that shows some structure, although this one will come up later as well for a good reason. Say it again. Well, these are different domains, so indeed the boundary conditions are different, and you'll see more visually how the boundary conditions are different in a couple of slides. Yes, the model is very dependent on the boundary conditions. No, these are not forced to be of the same color. You can come up with tilings where this will not be red. It's the probabilistic effect. With high probability, there will be the corner tiled by red. Yeah. So. Well, I mean, the left picture is for the square, and that's the boundary condition. But if you start playing with the shape of the square, you can create various things, but not immediately. No, to create this, you will need to do pretty drastic modifications to the square. But wait for the next slide, and then we can return to this question. So there is one more tool that makes visualization even more appealing. And the tool is that instead of looking at the planar picture, one goes into 3 dimensions. Okay? So rather than showing it on the pictures, I'll try to show the 3-dimensional simulation. So we have dominoes of 4 colors. And so I will lift them into 3 dimensions in 4 different ways, depending on the color. Okay? And so this is what I wanted to show. So this is the flat picture. And then once I look in 3 dimensions, so if I look from top, I only see the flat picture. But if I look in 3 dimensions, I actually see 4 three-dimensional shapes. Okay, so I'm rotating so that you can see what they are. Now, the reason for doing that, it looks a little arbitrary at the point, but the good property of what I've just done is that if you start with an arbitrary tiling of a planar domain, of a domino tiling of a subset of the square lattice, and then you replace each domino with this three-dimensional piece, then you will observe a plot of a continuous function. Okay, these three-dimensional shapes will stick together to form a graph of a continuous function. So this is known as a height function, and looking at and height functions are in one-to-one correspondence with tilings. So it's just easier to speak in terms of functions than in terms of the picture. Okay, so I will take this point of view. And then, so here is this simulation of a 100 by 100 Aztec diamond. That when I look at it in 3 dimensions, we see that not only there is a separating line between pure and non-pure colors, but there is actually a surface that shows up. So with high probability, the height function of the tilings will be near a fixed smooth surface. And that's the law of large numbers, or the limit shape phenomenon in this situation. Okay. So that's an additional dimension to the problem. I'm returning to my picture. So the Aztec is the bottom row, and the middle row is the square with the axis parallel to the coordinate axis. And then you see that what happens is that the plot of the height function is close to flat. It fluctuates around flat, but it's much flatter than the hyperboloid type shape of the Aztec diamond. So the boundary conditions in terms of the height function mean that for one square, the height function will be constant on the boundary. And for the other boundary condition, for the Aztec, the height function will be changing along the boundary as fast as it theoretically can. So these are sort of two very different possibilities, and partially explaining what we see in the picture. Okay. So the case of the Aztec diamond has been studied very well. People look at it for about 30 years by now, slightly more, and most questions have been answered. This is a very nice model to study. In a way, the simplest tiling model that allows exact analysis. So I'll listed a few results. It took years to find the difference between the earliest one, which is computing the total number of tilings of the Aztec diamond. It's a very nice number. It's a pure power of 2. So that's 1992 maybe. And then the final result on the list, the fact that if we look at the fluctuations of our random height function around the limit shape for the uniform distribution on all tilings, so that's given by a conformally invariant object known as the two-dimensional Gaussian free field. So that's probably 10 years ago or so. And then there are various questions one can ask from different scales. One can ask about the fluctuations of the boundary of this circle that people call the Arctic Circle. And the boundary actually fluctuates according to the Tracy-Witten distribution, which is a distribution coming from random matrix theory. There's a connection to random matrix theory. So this is a very well-studied playground. Now, I told you that I will only look at the Aztec diamond, and I just told you that everything has been studied about it. So what is this talk about? So the talk is about modifying the probability measure. So what has been studied extensively is the uniform probability measure on this big but finite set of all tilings of the Aztec diamond. I will instead put weights on my tilings. I will weigh my tilings in the following fashion. When I see a tiling, its weight will be the product of weights coming from the chosen edges. And on the edges of the square lattice, I will put their weights as some positive real numbers in a periodic fashion. So I will choose a box. So in this picture, it's a 4x3 box. I will put some numbers, arbitrary, on the edges in that box, and I will duplicate those numbers periodically left and right for the whole lattice. This will give me weights on the edges of the square lattice. And then once I see a tiling, I will multiply those weights And that will give me the weight of a concrete tiling. So if all my numbers are 1, I'm back to the uniform measure on all tilings. And if they're not 1, well, I get some other measure. Right? So the question is, what happens to my picture? And so the next slide shows the picture. So this on the left is the simulation over here. Again, there's a perfect sampling algorithm, so one can trust this picture as much as you can trust your computer to produce a sequence of zeros and ones independently. And you see that some things changed. Well, first of all, there are still pure colors on the corners. That's good. Now, but the boundary is no longer a circle. It's some strange curve. That's first things you mention, you notice. And then you look a little further, and what you see is that when you look at the planar picture, in the middle, there are some regions in the chaotic region which look different from some other regions. There is some difference happening in the middle over here. And furthermore, if one looks at the three-dimensional picture, if you turn, this is the three-dimensional picture. If you turn it around, you will see that these different regions in the middle, in the three-dimensional picture, become asymptotically flat. So our curved surface develops very flat faces, not perfectly flat. There will be small fluctuations around them. The fluctuations are actually of order 1. They're not growing. Small fluctuations around these flat faces. So this is the reason of the connection to the roughening phenomenon that I was mentioning. So what happens is that there are now crystal faces that showing up in our picture. That's a very flat, much flatter than the picture with the square that I showed before. Here the fluctuations are growing with the size actually, and here they're not. And then what happens around is, so here is the flat face magnified on the right. And then what happens around is some sort of a curved thing which fluctuates much more. Okay? So this is what you see with your eyes. And then you try different possibilities. So this is an example for 3x3 periodic weights. And then you play around. The algorithm allows you to do it, the sampling algorithm. And then you observe various possibilities. So this is a 3x3 on the left, and another 3x3. This on the bottom right is a 2x3. So you see that there is now a zoo of pictures. There are different pictures arise, and if you increase the periodicity, the complexity grows. So the simulation is showing you something. And so the question is, can we understand what it is showing? Okay, so the bottom line is that, what is this? Right? Just, yeah. The choice, the size of the domain and the choice of the weights in that fundamental domain. Very many choices. So, well, I chose some to plot. So this one is 3x3, and this one is 3x3, and this one 3x2. Exactly. Yes, the local change produces this type of yeah. So yeah. I mean, you'd need to be very, very lucky for that. Well, I mean, if you choose all edge weights to be, if you multiply all weights by a constant, you get the same measure. Typically, no. I mean, generic. There are equivalence classes. You can gauge transform your weight. There will be some integrals of motion. Yes, they will show up. And you can do transformations to the weights that will not change the measure. But if the measure changes, the picture will change. There is certainly a similarity with Goncharo and Kenyon, but they considered only measures on the torus. There is twice periodicity. There is a similarity in the microscopic definition, but the difference is that in this case, the domain has a non-trivial boundary conditions. In their case, it's on the torus, so it's translation invariant on large scale. They don't observe these kinds of shapes. In a way, yeah.
So if you make a choice of weights, here you can see an interesting picture.
Yeah.
Plus a random choice of weights give you again a useful picture that you have to
Yes.
play.
No, I don't need to play. No, I can put the weights, whatever yeah, these are actually generated with random sets of weights. And I could just tell the weights in a three by three region to be random between 0 and 5. And then you draw the picture and you see something like that. I mean, one of something like that. Right? Okay.
If it's not periodic and it's globally random, IID.
That's a different story. No, then you're not going to see this kind of structure. Right? I mean, we don't know what you can see. You can look at the simulation, and it's not going to show these flat regions in the middle. No, that's the phenomenon of periodicity. Yes, yes, these are Aztec diamonds, 45-degree rotated to fit better on the screen. Yeah, that's right. Yes, that's right. Thank you. Indeed, these are. I don't know if I have enough resolution to actually see the boundary. No, I don't have enough resolutions. Oops. Okay. So going for. Why am I? Okay. So the main message, if you don't get anything from this, I mean, if you get one thing out of this talk, which is the most I can hope for, is the message that the picture that you see here for periodic weights is actually an encoding of a Riemann surface. What you see here is a Riemann surface. Okay? There is an algebraic curve behind this picture, and you see that algebraic curve in some strange projection. Okay? So somehow probability knows about a Riemann surface. Okay? So now that Riemann surface will be defined by an explicit polynomial equation. So there is an algebraic curve. There is an equation in Z and W of a surface that lives in C2. And so I can't quite draw it. That's an abstraction. And so I need to somehow to move from here to here. The intermediary in that movement is something that's known in real algebraic geometry as an amoeba of the curve. You can take the set of all ZW satisfying a polynomial equation, and you can apply the log map. Take the log of their absolute values. That will map the surface in C2 into a picture in R2. This is the picture. It's called an amoeba because it sort of looks like amoeba. The term is due to Gelfand, Kapanov, and Zelivinsky a while ago, about 30 years back. And actually, in this case, the curves are particularly nice. They are in the class of Harnack curves as defined by Mikhalkin about 25 years ago. And what that means is that if you want to reconstruct your surface here, so this looks like a projection. But for Harnack curves, it really is not. You can go back. So for that, you take one copy of this amoeba, you take another copy of this amoeba, and then you glue them on the boundary. So you can imagine that you take two copies of this picture and then you glue them along these curves. You're going to have this sort of fat picture with holes. And that's this picture up to a map, up to a homomorphism, right? So this is really half of the Riemann surface. You really cut it like that, and you take a piece and then you spread it. Right? And then this picture, the amoeba, is an explicit diffeomorphism with a limiting picture on the dimers. So this outer curve here will be the frozen curve that separates frozen faces from the non-frozen ones. And then these ovals, the compact ovals, the bubbles in the amoeba, they go into these strange flat regions within the chaotic region. Right? So this is the most enjoyable part of the talk. It's just to tell you that what you see in probability is just really this. Okay.
This corresponding to the amoeba surface is topological or more. So do you just recover the genus, or do you recover some extra structure? And what happens with the cusps when you do the surface?
So there are two questions. So cusps here, they go to the tangency points. So this curve is going to be tangent to the sides of the square. And so it's exactly where these cusps are going to go.
When you go towards the surface, do you lose this information? The Riemann.
to the Riemann surface, well, in terms of the abstract Riemann surface, the position of these cusps are going to be just some points on. So if you look at the real part of this Riemann surface, on the real part, you're going to see this large oval over here, and that will go to the boundary here. So the cusps are going to be just some points on this big equator on this surface. Okay. So that I'm not claiming. I told you that the topological, I know I might, but I need to think about it. But topologically, you can restore it by gluing two copies of it, right? K and L are the periods. So if you have 3 by 4, K and L are 3 and 4, and so the genus is going to be 2 times 3, which is 6. This is the Newton polygon. So this is a 3 by 3 periodicity. And so the Newton polygon actually has a direct relevance. So if you look at this picture, and if you look at the, so this is a surface, right? Imagine it's a three-dimensional surface. So on this surface, you can compute the two partial derivatives, right? d over dx and d over dy. Two numbers, the gradient. Well, right. The gradient of the function whose plot you're drawing. So if you map this object to the point which gives you the two partial derivatives, the image is going to be a square. And this is actually the Newton polygon of the corresponding polynomial over here. And so the corners here are going to be the frozen faces. So this is where the gradient is extremal. This is where, so in my three-dimensional representation here, you see that in the frozen faces, our surface is very steep. So this is the position where the gradient takes values in the corners of the square over here. And then the bubbles, these facets, their gradient actually will land into the integer points in that square. And the whole gradient of the whole picture will fill this square. So there is an additional layer to that picture. Also, there was a question of whether one can recover some more structure here than just the contours. And the answer is probably yes, but we are not there yet. So the fluctuations here should be governed by a conformal invariant object with the conformal structure coming from the spectral curve, coming from the Riemann surface, but that hasn't been proven. It's supposed to happen, but there's work to be done. Any other questions before me? Maybe, I don't know, but that's not the way we approach. I mean, that might define you but the conformal class is not difficult. What you want to prove is that you want to go to a particular 2 points, look at the fluctuations, and find their correlation. It's still okay. Let me not fantasize about what hasn't been done. So in the case of the uniform measure on the Aztec diamond, you just get the Gaussian free field on a disk, on a simply connected domain. So it's supposed to be a Gaussian, so it's probably in the chaotic region, so not including the facets. It's going to be some variation on the theme of the Gaussian free field in a non-simply connected domain, which is like half of this Riemann surface. But that Gaussian free field probably will be modified by some lower order corrections, and that needs to be computed. On a non-simply connected domains, the fluctuations are probably not pure Gaussian free field. They also have certain discrete monodromies around holes, which one needs to study. We can talk more about it. It goes way beyond what I want to say. Okay. Right, so this is a little bit of an extension of the map. So I told you that there is a diffeomorphism between the shaded region over here and the complement to the facets over here. But one can also extend that diffeomorphism to the boundary. And so what will happen is that there will be a map between the boundary of my amoeba, which is on the right in this cartoon, and the boundary separating the flat regions from non-flat ones in the Aztec. And so that map actually preserves the slope of the tangent line. The slope of the tangent line in this picture is encoded by color. So points of similar color go to same color, and that also preserves the slope of the tangent line. So here and here. The only difference is that if you travel around the curve here and here, you go in opposite direction. So like you go clockwise here and you go counterclockwise there. And that in particular will tell you that any of the flat regions inside will have exactly 4 cusps. Why? Because you start with the compact oval here. You go around the compact oval. You will gain 2 pi when your tangent line travels, and then you will take the same tangent line and you will travel backwards. So that will give you another 2 pi. The 2 pi and the 2 pi will give you 4 pi, and that 4 pi needs to be compensated somehow, and it gets compensated by 4 cusps, in each of which you get a jump of pi. Okay, so what I'm saying is that each of the flat regions over here, I'm not sure how visible it is, but it's actually of the shape of a star with 4 cusps. That's a nice corollary. All right, I think I'm doing well. So what's the connection? So how can probability and dimers can produce Riemann surfaces? What's behind that? So the rest of my talk is an attempt to explain why the two things are, well, closely connected. Okay? So I will talk about 2 ways to get from the probabilistic model to a Riemann surface. One is more general. It applies to essentially arbitrary domains, planar domains and arbitrary graphs. It's a general principle that has been known for probably 150 years since Gibbs. It's often referred to as the Wolf principle or Wolf crystal. And it says the following. That the limit shape that one observes in our problem, so this saddle-like object here, or the analog in the periodic case, must be a solution to a certain variational problem. Okay, so there is a way to set up a variational problem. The boundary conditions will be provided by the shape of our domain, or, well, which is the same as the values of the height functions on the boundary. And so if you manage, and that variational problem will have a unique solution, and that unique solution will be the limit shape. So in an absolute, so with very high probability, the random realizations of your model will produce functions in an epsilon neighborhood of that solution. Right? So this is the overall mantra. Now, why this should be true? What is the variational problem? So to imagine how this works, so the limit shape is the shape in the neighborhood of which you should find the most possible, among all possible limits, among all possible height functions of your dimer models, most should live in the neighborhood of the limit shape. Right? That's the law of large numbers, concentration of measure. So let's take a surface and let's count how many height functions can live in a neighborhood of that surface. Okay, so that will be our functional whose maximum will be reached on the limit shape. So how do we count? Well, we take our surface, we cut it into pieces, which are much smaller than the surface, but much bigger than the lattice size. So these pieces of our surface is smooth enough. These pieces are going to be approximately flat. So let's fix our dimers or our height function on the boundary of these pieces. And then let's see how much freedom we have on the inside. Right? So we're fixed on this little rectangle, we fix the boundary. And then inside we have freedom in choosing our dimer. So let's see what happens. Now what got simplified? What got simplified is that in each piece, the boundary conditions are approximately flat. So the problem is closely related to the square that I started with, where the x is parallel to the coordinate axis. When in the flat situation, it's actually possible to write a formula for the number of dimers in a domain like that. So for a flat piece, you can compute explicitly the number of dimers. This is the formula for the square. It doesn't look like it's an integer, but it is. And you see there is a product over all roots of unity, which tells you that there is actually a little Fourier transform computation that does this thing. And that works for piece of any slope. So that way, you know how much or how many things you have in the neighborhood of each of the small tiles. Now you can take the product over all of these small pieces. That will tell you approximately how many different height functions you have in the neighborhood of your surface. You take the log, that becomes the sum gets turned into the integral when the sizes of these go to infinity. And so that tells you that there is an integral functional whose maximum should produce the limit change. So the surface is always Lipschitz because the pieces out of which it's built are Lipschitz. I mean, the height function cannot be wild, so that you know a priori. That helps a lot. I mean, you're immediately in Lipschitz functions. All right. So the functional itself. So that's what I told you. The computation of this computation. So this computation, this is for uniform measure. So the total number of dimers of dimer covers of the square is this. All edge weights are 1. So when edge weights are not 1, that's a harder computation. It's a very nice computation, and that was done about 20 years ago by Kenyon and Quinkova and Sheffield. And so that's where the algebraic curve first appeared. So there is on this slide, there is an answer for what this functional, the one that computes the freedom for a flat piece, how many tilings there are in the flat piece asymptotically. That piece is known as the surface tension, or the free energy in physics language. And so that has been computed in terms of a certain polynomial. So the polynomial in two variables, the P of ZW, that's the one that describes our Riemann surface. That is directly constructed out of our weights, right? On the input, we have the weights on our dimers. So here is our fundamental domain. Here is our weights. Somehow on the edges, we have these weights. Now we're going to wrap, so I will try to explain how this comes out from this. Right? I need a polynomial out of the set of weights. So I will wrap my fundamental domain on a torus. Yeah. I mean, for this picture, yes, but the probabilistic meaning is not going to be there if they're negative. Yes, I mean, the determinant, I don't have a, well, there is a determinant over here. There is a determinant, yeah. But there is also a way to say it without the determinant. And if you wrap the fundamental domain on the torus, and then you choose two loops on the torus, two generating loops on the torus, and then for every edge that crosses these two loops, you add a variable. So for one loop, I'm adding W, and for the other loop, I'm adding Z. So then if I take the sum over all possible ways to tile my torus, weighted by powers of Z and W, according to how many edges cross these two loops, I will get the polynomial in Z and W. And that's the polynomial we need. There is also a way to write it as a determinant. So this is a determinant of a matrix with rows and columns parameterized by white and black vertices. And what sits here is just essentially the edge weight of the corresponding edge, or 0 if the two things are not connected. Right? So there's an explicit procedure that produces a polynomial in Z and W out of my fundamental domain. And so that's the relevant polynomial. That's the polynomial that defines the algebraic curve. So what Kenyon, Okunkel, and Sheffield did, they computed out of this polynomial the surface tension. So this is, I'm not going to go too much into it. This is Legendre transform of this expression here that involves the polynomial. There are two integrals here around circles. This is coming from, again, for the Fourier transform. There is a discrete Fourier transform that's relevant in the computation. That's a generalization of this kind of formula under the log and the limit that one gets. I mean, it's a very nice, and it's already sort of tells you that there are, depending on the geometry of this curve, that there are regions in which free energy behaves differently. And so they already had the amoeba in their work. Now, right. So that tells you that there is, so backtracking, that gives you a variational problem. And you know that if you solve the variational problem, you know what the limit shape is. The question is how to solve the variational problem. Well, that's difficult. There are no algorithmic tools at the moment to solve that variational problem. The problem is there, but the solution is not. If someone gives you a solution, you can verify that the solution satisfies the Euler-Lagrange equation, but even that is not the end. The problem is that the solution is not smooth in the whole domain. Here, where the chaotic region meets the facet, there is actually the smoothness has finite order. It's like 3/2 or something like that. So one needs additional considerations to the Euler-Lagrange equations to tell you that you actually have a solution of the variation. I mean, you have the global maximizer, and that's not easy. So there are separate analytic tools that one can employ, and people are on top of that. But even if one manages to do that, it's still not clear how to produce that solution, even for simplest domains. Okay? So the advantage in choosing a domain like the Aztec diamond is because it has additional algebraic structure behind it that allows one to get the solution out from something else. Now, that something else is a techniques that's coming originally from, well, random matrix theory and a different field of mathematics, the theory of integrable systems, or more concretely in this case, the finite gap method of integrating integrable partial differential equations. So that's a long story, but I will try to give an example of what the relevant piece is and how it works. I still have a little bit of time, so that's what I'll do. It's not going to be obvious, if you haven't seen it before, how this piece is connected to what I talked about before. But this is the integrability piece that makes it possible to find the solution for the Aztec diamond. Aztec diamond at this moment is the only domain for which we know the solution for general periodicity, actually for any non-trivial periodicity. And there is something inside that makes it possible to produce it. Right? So what's the inside? So here is an elementary problem. Right? This is a problem in linear algebra, not even a hard one. So take two matrices. So here, two 2x2 matrices. They have a complex variable z inside. So there is a z here in the top right corner. In the second matrix, there is a z in the bottom left corner. What I want to do, I want to take the product of these two matrices, and I want to write it as a product of two other matrices in such a way that the singularities in z swap. So this matrix on the left had some zero of the determinant in z, right? The determinant is a linear function in z. So it vanishes when z is something. Now I want that zero to move to the right. And I want the zero of the determinant in z here on the right to move to the left. If I were in a Abelian situation, I'd just flip the two factors of a polynomial, that's it. But for a matrix polynomial, that's a non-trivial operation, to flip the two factors when with the roots staying the same, right? Well, for 2x2 you can do it. That's an explicit formula that does it. There is a x here, and that's computed in terms of my constants alpha, beta, gamma, and so on. Okay, so the task is somehow the algebraic techniques from random matrices tells you that if you manage to run this dynamics for a very long time and you can control what happens, then you will know how to solve the original diamond problem. So what do I mean by dynamics? I started with two matrices of a certain form. I got a new matrices of the same form, right? This is like this and this one is like that, but the coefficients are different. I want to keep running it. I want to run it a million times. I want to know what I get. It's a nonlinear transformation. What do you do? And the computer chokes up pretty quickly. So the achievement from a long time ago, dating back to the first papers, date back to mid-70s, the so-called finite gap method, actually tells one how to write solutions to this kind of dynamical systems. This is an integrable system. So these are essentially, so if you take the Aztec diamond and if you slice it, you can write the transfer matrices between different layers. And these are infinite matrices, but if you go to Fourier transform, if your periodicity is 2 by 2, you will get 2 by 2 matrices with a Fourier parameter, which is Z in this case. So these are essentially Fourier transform of transfer matrices between layers of Aztec diamond. Okay. I can give you more details, but it's going to take a while. Yeah. What is not the same? Well, I could have made an error. Well, let's check. So Z here is something like alpha delta divided by gamma beta. Now, the claim is the zero of this matrix as a function in the zero of the determinant of this matrix as a function in Z has to be the same as here. Not the eigenvalues of the matrix, but the singularity in Z. Well, by eigenvalue, I really mean where it vanishes as a function in Z. Yeah.
So that is not an eigenvalue of these matrices, but of some. Why
No.
call it eigenvalue?
If you have a matrix polynomial, so a polynomial that has a variable Z, you take a determinant of it, you get an ordinary polynomial. It has zeros in Z, and people sometimes call it eigenvalues when they're dealing with matrix polynomials. You can call it. It's not a traditional, I mean, if your polynomial happens to be the characteristic polynomial of the matrix, then it's going to be the eigenvalue of original matrix. Yeah.
So people by mistake do that, we should not repeat that mistake.
You are free to repeat it or not. I chose to repeat it, so, sorry.
But you see the damage it creates, so anyway, now I understand. So zeros.
If you can come up with a better term, I'm happy to use it, but it's not so easy. Zeros of a matrix, I mean, zeros of a matrix polynomial, but it's not really a zero of a polynomial, it's a zero of the determinant of that polynomial. There is no perfect term here, so so you choose the one that does less damage, right? Okay. So I wanted to say quickly why this dynamics is integrable. How is it integrable? So the trick, there are lots of letters in the slide, but let me try to say it in words. So if you have that dynamics, if you look at, these are my two matrices, and when we take the product, this is a matrix polynomial that has a Z and a Z inverse. And so my dynamics is conjugating this polynomial, right? The flipping of two matrices is a conjugation operation. The conjugation doesn't change determinant, but it also does not change the characteristic polynomial of a matrix. Right? So if I write the characteristic polynomial of the matrix, so that's going to be determinant of P of Z minus W, this one, that doesn't change under my dynamics. And actually, the coefficients of the characteristic polynomial have all the integrals of motion in my dynamics. So if one looks at it as an integrable dynamics, then this is what the invariant is. Then, if you look at the curve where the characteristic polynomial is 0, then there you must have a null vector, right? If a determinant of a matrix is 0, there is a null vector. Well, which is the same thing to say, is that I'm looking at the eigenvectors of my matrix. So instead of instead of looking at the dynamics on the matrix itself, I'm going to look at the dynamics at what it induces on the eigenvectors. So an eigenvector, which I call psi here, depends on z and the w. So z is the same as z here, and w is the eigenvalue. Right? And z and w must vary on this curve, right? Because the solution needs to exist. The key property that makes the integrability possible is that one can see how the singularities of this function in z and w evolve under the dynamics. So in my case, this is a 2x2, this is a size 2 vector function, so 2 scalar functions on this curve. They're meromorphic. They will have zeros and poles. There are lots of things known about zeros and poles of meromorphic functions on algebraic curves. In particular, the number of zeros is the same as the number of poles. That's 1. But then the other one that's much more relevant to us is the so-called Abel theorem that tells one that there is a map of the algebraic curve to a torus called the Jacobian of the curve, such that in the image, the sum of zeros minus the sum of poles must always give 0. As it happens here, when I look at my vector as I evolve it, I will be able to know a priori from the structure of my matrix what happens to almost all zeros and poles except for 1. But Abel's theorem is going to tell me that the sum of all of zeros and poles is 0. And so that will tell me what the final one is. And that allows one, and that actually shows that the flow, this flipping flow, the refactorization flow, is a linear flow on the torus, which is to which the curve is being mapped. So this is the integration of, well, in this case, a finite dimensional problem, but it was originally applied to infinite dimensional problems like KdV equation. And that's the essence of the finite gap method of integration. As I said, goes back to 1970s. Novikov, Dubrovin, Krichever, there are lots of people who contributed. This psi is known as the Baker-Hieser function, and there is sort of a large literature around this. Disconnected from what I talked about before. Well, has been disconnected so far. Okay, this slide just explains what I said in words about zeros and poles more concretely, but I'm going to skip it. I'm happy to tell you in details after the talk. This slide is just a show-offish slide. So this refactorization procedure, right? You take my matrices, you put them in the wrong order, and then you refactorize, keeping some property. And then you put the wrong order, and you refactorize, and you keep going. So this type of refactorization is actually all over math. So there are these are three places which are much more important than what I talked about in math in general, where similar type of dynamics show up. So the first one is the QR algorithm of finding eigenvalues of a matrix. It's run by computers billions of times, probably every day. So one takes a matrix, factorizes into an orthogonal and triangular one, and puts them in the wrong order, factorizes again, wrong order, factorizes, and so on. If you do that, mostly you will converge to a triangular matrix with the same, of course, the eigenvalues will stay the same, and so you can read them off the diagonal. Right? So that's a very efficient, stable algorithm of numerical linear algebra. Billiard, so if one takes an ellipse or a three-dimensional ellipsoid and shoots a billiard and wants to trace the trajectory, so that's an integrable system that's solvable by matrix refactorization as well, and that's actually possibly the one that made Jacobi introduce elliptic functions. So that's one of the first integrable systems ever, maybe the first one, the non-trivial one that has been solved. And one can also discretize equations of the body of the rigid body motion, and that's also a matrix refactorization thing, it turns out. And so the fact that we were able to solve this refactorization problem is not a local miracle, but a global one. It stretches a few centuries. All right, I think I am done. I had the pleasure of writing a summary by just drawing a pictures, or rather copy pasting them from previous slides. So, and I'll stop here. Thank you very much. The previous slide, yeah, this one. I can also send you the slides.
Great talk.
Thank you.
Any questions?
What if you look at the lozenge tilings with the same periodicity? Is it the same? Is it solvable the same way?
Right, so you need to fix the domain. So if you look at the lozenge tilings, I had one picture of them just show up. Let me go back to that picture. So lozenge tilings is a similar game, but not on the square lattice, but rather on the hexagonal one. Right? So here is a picture. This is a lozenge tiling of a hexagon, of a regular hexagon, and this is a three-dimensional surface associated to it. So many of the same things apply. In particular, you can introduce the periodic weights. And one certainly, well, Kenyon-Okonkov-Sheffield tells you the computation of the surface tension. So there is also a curve and an amoeba, and one expects similar phenomenon for the limit shape, not done. Okay, so hopefully it will be done. Not completely everything is the same. In particular, so we have these four-corner stars show up in our picture. So in this case, there will be parameters for some sizes of the hexagon where the stars will have 6 corners. At least that's what we think we know. People are working on this. Nothing published yet, no results. This is a harder case than the Aztec diamond. As I said, Aztec diamond is really the simplest non-trivial domain that one can look at. So there should be results. I'm sure there will be results, but none of them are there yet.
Any other questions?
Can you please show the slide where it was f of xy, like free energy slide?
The free energy, the value of the free energy. This one, yeah.
Yeah, I mean, so I'm confused because it's function of x and y. I mean, I suppose the energy should be number. So I'm not sure what you're minimizing.
So, okay, so the free energy is a function of the slope. Okay, so the free energy tells you essentially how many tilings you have once you fix the boundary conditions in a flat way so that your surface approaches a plane of a certain slope. Okay, so this is what was happening on the previous thing. So when I cut my surface into pieces here, the pieces will have different slope. And so for each slope, I need to know how to compute the number of possibilities in the neighborhood of that little piece, okay?
So it's a density then, right?
Hmm?
I mean, I'm used to fact that you should have a number and then you have to do variation over number.
So here, the surface tension is a function for slope. So sometimes the free energy is just a number. For some models, there is only one infinite Gibbs measure, and so there is only one number, which is the free energy. Okay, so in this case, the local Gibbs measures, or the translation variant Gibbs measures for the tiling model, they come in two-dimensional family. And so for each member, there is its own surface tension.
So xy is not a slope. Is it a slope?
Xy is the slope.
Yeah.
Yes. Xy is well, actually no. Xy are two arguments of this thing, which is known as the Ronkin function. So xy is actually a point in this picture here. So you get the function on top of it, which is a convex function. So Ronkin function is going to be linear in the pieces that are not shaded and curved in the pieces that are shaded, and it will live on top of this picture. And so when you take that convex function and you take its Legendre transform, then you get the surface tension. So there is some work to get to the free energy.
If you can say it fast, what is minimization problem here? If you can't, I can ask you later.
The minimization problem is that you integrate a function of a slope over this surface. The function of a slope is the Legendre transform of the function that I have on the next slide. Yep.
There are two algebraic curves appears in your talk. One is in the next slide, which is the special curve generated by the base structure, and the other one is which appears in the factorization of the two metrics.
It's the same curve.
It's the same curve.
It is the same curve. Yeah.
Okay. So, but for this curve, it looks like W and Z actually have the same, have a similar situation, that it should be some like bi-quadratic or bi. But that one is PZ minus W, which looks like W and Z plays different roles.
So what right? So if you look at this one where Z and W play similar role, again, if you slice this picture into layers, I mean into transfer matrices, you can actually write the condition that, so if you want the condition that the determinant of P of ZW is or right, that P of, sorry, the P of ZW is 0, that's a condition that when you multiply the transfer matrices over you go through that, and then you multiply by Z in the end, and you circle around, you get to the same place. You need to have a null vector. Right? The determinant of this matrix is going to be 0 when you have a null vector. So when you write that condition in an asymmetric way, like you start with the values of your null vector on top, and then you propagate them all the way to the bottom, and you circle around, then this will be a non-symmetric condition in Z and W, and you will see that condition is equivalent to the other spectral curve that I put over there.
Okay,
so
thanks.
that there is a slicing that goes from one to the other. Thank you.